In this video, we'll take a look at torque. A torque is a force that causes an object to rotate around some central point. There's lots of examples of torques in the real world. In this picture, we have this little boy in the blue shirt applying a torque to the merry-go-round, causing the merry-go-round to rotate around this central axis, this central point. The boy is applying a force to the merry-go-round, creating a torque here at the center. This man pulling on the wrench. As the man pulls on the wrench, applies a force to the end of the wrench, is producing a torque here on either a nut or a bolt, causing it to rotate around some central axis. The man applies a force to the wrench applies a torque to the bolt. And then finally, my last example, these children playing on the seesaw. These children apply torques to either end, causing the seesaw to rotate around this central axis right here in the middle. Again, the world is full of torques. Anywhere there is something rotating around an axis, there's been a torque applied to make that object rotate around that axis. What torques do is they cause angular acceleration. They cause the angular velocity of the object to change. The object was sitting at rest, and it was forced to rotate around some axis, causing its angular velocity to change. So imagine here is the nut or bolt that the wrench is torquing on. Originally, it was sitting here, and it was caused to turn. It was caused to go into motion, to accelerate in this direction. We created some kind of angular velocity when there wasn't one to begin with. That is acceleration. The amount of torque that you get depends on two factors, the force and the radius. Force and torque are directly proportional. This means any change in force will cause an identical change in torque. So if you double the force that's acting on an object, you will double the torque that is being applied. So if you double the force on the end of the wrench, it will double the torque that's being applied to the nut or the bolt. If you cut the force in half, you'll cut the torque in half. So if you cut the force that's acting on that wrench in half, you'll cut the torque that's being applied to the bolt in half. Radius and torque are also directly proportional. Again, any change in radius causes an identical change in torque. So if you double the radius, which is basically the distance between where the torque's applied and where the force is applied, if you double that radius, you would double the torque. So if you doubled the length of your wrench, you would double the torque that's being applied to the nut or the bolt. This is why torque wrenches tend to be rather long wrenches. If you cut that radius in half, in other words, use a wrench that's only half as long, you would have the amount of torque that's applied to the nut or the bolt. Makes it very important to choose the right length wrench. If you're trying to apply a torque to a relatively small bolt and you use a wrench that's too long, that long radius will produce a strong torque which could snap the head off the bolt. At the same time, you wouldn't want to use a wrench that's too short on a bolt that needs a high torque. You wouldn't be able to apply a strong enough force with a short radius to produce the torque that's needed. So choosing the right length wrench is a rather important thing when it comes to mechanics. Both variables are directly proportional to torque, therefore both will appear in the numerator of the equation. Remember, anytime there's a directly proportional relationship, when we look at the equation that contains those variables, we'll find those variables in the numerator. If it's an inversely proportional relationship, you'll find those variables in the denominator. Forces, F, are measured in newtons in the metric system, and radius is typically measured in meters in metric. So when we combine the newtons and meters together, we basically just get a unit called the Newton meter, capital N, lowercase m, Newton meters. Torque does exist in the English system as well. In the English system, the force is measured in pounds and the radius is measured in feet. So you get pound-feet or foot-pounds of torque. This is an important number when looking at the power of engines. So many people get caught up in the horsepower of an engine. Horsepower indicates how much output that engine has, but an equally important number is the torque. This is a screenshot of the Chevy Corvette website, and you'll see right here the 650 pound-feet. That's the torque that's being applied by the engine. And that torque is a measurement of how much power that engine has of turning the wheels to actually make the wheels spin. So when you want to talk about top speed of a car, that's typically horsepower. When you want to talk about how well a car accelerates 0 to 60 times, that's mainly a product of the torque. Pickup trucks are designed to have a lot of torque. The torque they produce allows them to haul cargo. So again, it does exist in the English system, and our English systems our unit would be pound-feet. Let's take a look at how that math works with these relationships, starting off with the relationship between force and torque. A 2,500 Newton force is applied to a 0.75 meter wheel. How much torque is produced? So 250 newtons is a force, so that is F. Question becomes, what is the 0.75 meters? Typically, when you're measuring a wheel, as in on a car, or a gear, or a pulley, that number is the diameter. So when we say 0.75 meter wheel, that is the diameter of the wheel. We're going to need radius for this, so we're going to need to cut that in half. So we're going to use 0.375 meters as our radius. We're looking for torque. The equation is torque equals force times radius. The force is 2,500 newtons. The radius is 0.375 meters. Multiply those two numbers together, you get 937.5. And again, the unit is just Newton meters, NM. Now let's do a little thought experiment here and see what the torque is going to be if we double that force. We will double the force to 5,000 newtons. And if it is truly a directly proportional relationship, and if our equation is set up for the directly proportional relationship, we should see the torque double. So 5,000 newtons, that's our force. 0.75 meter wheel, that is a diameter. Again, we need radius when we do the calculations, so we need to cut that in half to 0.375 meters. We're looking for torque. Torque equals force times radius. The force is 5,000 newtons. The radius is 0.375 meters. 5,000 times 0.375 is 1,875. And again, Newton meters just get combined together for the unit. So what happened was we started off with 937.5 Newton meters of torque. We doubled that force, and that caused a doubling in our torque. We see an identical change because it is a directly proportional relationship between force and torque. So again, doubling the force from 2,500 newtons to 5,000 newtons doubled our torque from 937.5 to 1,875 newton meters. And this makes sense. A bigger engine can produce more force. That greater force results in greater torque for each of the tires. A stronger person pulling on a wrench can produce a stronger force on that wrench, producing a stronger torque on the bolt they're trying to turn. This is the relationship that makes sense. The one that we have to learn a little bit more about, because it's not really covered anywhere else in high school curriculum, is understanding how the radius part works in that directly proportional relationship. So let's start with the math and just go through a hypothetical situation again to see how the math works. A person applies a 20 Newton force to the end of a 0.15 meter wrench. What torque do they produce? So the force is the newtons, the 20 newtons. And this time we're talking about the length of the wrench. And the length of the wrench goes from the axis of rotation out to where the force is applied. So when you're talking about the length of a wrench, you are talking about a radius. So the 0.15 meters is the actual number we need this time. And again, we're looking for torque. Torque equals force times radius. The force is 20 newtons and the radius, the length of our wrench, is 0.15 meters. And again, this assumes that we are pushing all the way on the end of the wrench. If you were not pushing all the way on the end of the wrench, that would change your radius. 20 divided by 0.15 is 3, or multiplied by 0.15 is 3. And again, the newtons meters just combine together to make that new unit. Now what we're going to do is we're going to double the length of our wrench. Instead of a 0.15 meter wrench, we're going to have a 0.3 meter wrench. And we're going to see what happens to our torque. Again, the 20 newtons is the force. 0.3 meters is the length of the wrench, and that does go from the axis of rotation out to where the force is applied. And again, we will assume that we're going to apply the force all the way on the end of that wrench. We're looking for torque. Torque is force times radius. The force is 20 newtons. The radius is 0.3 meters. 20 times 0.3 is 6. And again, newton meters for the unit. So when the length of the wrench was 0.15 meters, we had a torque of 3 newtons. When I doubled the length of the wrench to 0.3 meters, I doubled the torque. Again, mathematically, this shows us a directly proportional relationship. The way we changed the force was identical to the way that the torque changed. Now, understanding why involves a little bit more background than what you may already have. So again, doubling the radius from 0.15 meters to 0.3 meters resulted in a doubling of the torque from 3 to 6. Again, it's harder to understand because you have to understand simple machines. There are 3 basic types of simple machines. You have levers, wheels, and axles, and you have inclined planes. And there's nowhere in the science curriculum in the state of South Carolina where those are actually taught anymore. What this is taking advantage of is the wheel and axle system, a wheel and axle simple machine. And basically, a wheel and axle is just 2 circular objects rotating together. Very simple machine that multiplies the force that's applied to your object. We have 2 interconnected circles when we're dealing with applying a torque. There's going to be a circle that's produced by the applied force, and there's going to be a circle that's produced by the torque. The applied force circle is way out here where you apply your force to the wrench. The torque circle is in here in the middle where the wrench is applying its force to the nut or the bolt. We have 2 circles that are rotating together, 2 interconnected circles. And the way this is set up in a torque is that the applied force circle is larger than the torque circle. The circle that's being made by the applied force is larger than the circle that's being made by the torque. And when this happens, what you get is a multiplication, an increase in the force that's being applied here on the torque circle. It's a basic simple machine, similar to a lever, but there's nothing on the other side of the axis of rotation like you typically get with a lever. You're applying a force out here and you're moving a larger distance. The torque is going to move a smaller linear distance, and the payback for that smaller linear distance is the increase in force. That's generally the way simple machines tend to work. You move a greater distance, and as a result of moving the greater distance, you're rewarded for that with an increase in force. All simple machines basically work the same way. The larger the radius of the applied force, the larger the force you're going to get, the bigger the increase is. It's the same thing that works in a screwdriver. When you try to turn a screw by hand, literally putting your thumb and your finger on the screw itself and try to turn it, you don't generally get very far because the circle that's being produced by your applied force is pretty much the same as the circle that's being produced by the torque. You're getting no mechanical advantage, as we call it. So whatever force you're applying is identical to the force that's being applied by the torque. There's no multiplication of force happening there. When you use a screwdriver, you're turning the screwdriver up here. And the radius that you have up here is considerably larger than the radius that you have down here where the torque is being applied. So in other words, your hand is going to produce or move in a larger circle when you apply your force than the torque circle. And because your circle up here where you're applying the force is larger than the torque circle, you're going to get an increase in force. You're going to get a multiplication of force that happens. Again, that's the way this simple machine system works. And that's why increasing the radius increases the torque that's being applied to the object. You're not providing any stronger a force than you could otherwise. You're getting the exact same force. It's just that that simple machine that's being used there is increasing that force because of the larger distance, the larger circle that you're going to have to travel through. I'm not going to go into the unit conversion stuff and doing math problems with the unit conversions. We've done plenty of those through the course of physics. If you're asked for a force in Newton meters and you're given a radius in centimeters, do make sure that you do conversions before you do the math. I have a whole video on metric conversions, and you can look at almost any other video on here and see examples of questions where there are unit conversions due. Watch for those. And then also remember, there's times when you'll have to use other equations to find missing information. So we might be using an equation to figure out what the force is before we can do the torque equation. Or we're figuring out what the radius is with some other math before we can calculate what the torque is. Be aware that that does sometimes happen. That's why we always want to list out what we're given and what we're trying to find. Look at the equation that will give us our answer, look for missing things, and try to come up with a game plan of how to find those missing things. So all the little tricks and twists that we use in physics to make problems harder can be applied to these just the same.